The history of BCI may be already over decades, if not 100 years, from the first signal you measured from monkey spread. But globally, BCI is in a very critical stage. Moving forward very rapidly from lab experiments to real-world application, especially in clinical applications. So in recent years, especially in the recent 2 to 3 years, including our team, I think there are many very impressive progress. For example, like Neuralink, founded by Elon Musk, has shown very promising progress in restoring motor control. For example, he can have the patient who was installed with this kind of device can use his mind or her mind to control this physical equipment, for example, wheelchair, robotic arm, and so on. And also they can use their mind to control digital equipment, for example, to connect to an iPhone, a pad, a computer, or video game, to play video game or do some web browsing. And our team, which is NeuroXess, can do something similar in terms of motion control. In addition, we move a step forward so that in addition to do this motion control using mind, while BCI, we can also do language decoding, which means we can use BCI to translate the patient's mind into text, especially in Mandarin, so that you can have that patient to either play video game or directly interact with other people like a normal person, or you can even have this patient can interact with LLM, which is large language model, so that it can benefit a lot from this device. So basically, a lot of recent progress are more focused on the clinical part. So especially towards those patients, for example, ALS patient or spinal cord injury patient, so they can have the ability to communicate and to interact with the environment.
Mm-hmm. And now patients need to be connected to devices or implanted electrodes. How far are we from making BCI just easier for patients?
This is going to include different factors. For example, A is the device itself. If it's universal to different applications. So that's one thing. Another thing is, about the implantation itself. If the surgery or the implantation process is easy enough or robust enough and reliant enough for implantation to many other patients. And the last part is after implantation, how fast the patient can get used to this implantation and can to use that to interact with other people, interact with the world. So in my estimation, I guess for a very severely damaged, in terms of the brain function damaged patient, is going to take probably another 2 to 3 years for these patients to have this device and to be able to do motor and language restoration close to normal person level. In the long term, for example, if we can further minimize the damage during the implantation and increase the reliability in terms of long-term stability of this device, it might take a little bit longer, I would say probably 5 to 10 years, so that you can have this implantation is much easier, and you're going to see much more patients or users can benefit from this technology. So we say short-term 3 to 5 years, long-term 5 to 10 years. Yeah.
And you just touched upon that there are mainly two approaches to BCI, invasive or non-invasive, but invasive implants offer higher quality of the signal but come with surgical risks. And for invasive approach, what do you do? What kind of new materials are you exploring at this point?
For invasive devices, you have to deal with the problems or the challenge of, for example, safety, the durability, the signal quality, and the long-term stability. And all this eventually decided by the smart choice of materials, because this is an implanted device, so the material selection is the key thing here. So especially for this implanted device, many groups, including ourselves, we are choosing the material format as flexible, device. So in order to make this flexible device, you have to make them as thin as possible and as robust as possible after implantation. So the material itself has to be mechanical strong, and it has to be biocompatible, and it also has to be compatible to micro-nano manufacturing process. So that's some key requirements of the material. So in our case, we select silk protein. The proteins we extracted from silk cocoons. So this material, silk fiber may be one of the most strongest fiber you can find in nature. So this protein you extract from silk fiber can have this great mechanical properties from this fiber. So we can make the flexible electrodes much thinner, but still maintains mechanical strength. And also silk proteins and natural proteins very biocompatible. So after you implant this into the brain, and the brain can still stay very low response in terms of the immune response. So and there are many other choices, but we stick to natural protein, and so far so good.
And now we have been just talking about patients, and you also said that BCIs can also enable superhuman performance. Can you elaborate on that, please?
That's my goal, and I'm a believer of that, because I was thinking about two questions. I mean, why human beings so strong compared to other species, for example, like dog, monkeys, and other animals? Because that's because our brain is the most advanced part of our body. Our other parts, for example, our limbs, we only have 2 arms and 2 legs. There are many other animals that have more arms, more legs, and have more strength and high speed than our arms and the legs. Because in this case, if we can use BCI to bypass our other body parts, directly connect our brain to, for example, robotic arms, and other silicon-based technology, so that they can surpass our own abilities. So that's the goal we're looking at. So that's why I always thinking BCI is actually the way you can merge human intelligence and artificial intelligence and the embodied intelligence, so that you can use the best part of our human beings, our brain. But for the actuator, for the sensors, we have much better sensors, actuators enabled by modern technology. For example, other sensors, robotic arms, and mobile phones, and so on.
And also, how big is the market? When do you think the technology can be commercialized?
Yeah, I think it won't just be big. It will be a game changer. It's going to create an entirely new ecosystem, like what we have seen before, like the internet or mobile phones, or even better. So the market, it's going to affect every part of our daily life. But in terms of which sectors we're going to see BCI gonna thrive first, I would say probably 2 sectors. The first is the research market, because there's more and more research group and academic force that gonna investigate how our brain works. So they're gonna have some BCI tools, equipment to help those scientists to understand better how our brain works. So that's the first sector, and we are seeing an increasing market for that part. And a much more important sector, and a much larger sector in terms of market, is the medical. It's the clinical market, and I, including our group and many other groups, we are working very hard in terms to try to make BCI product as a medical device, so that we can have those people that suffer from motor or language loss, so that they can restore their ability. For example, ALS people, or like spinal cord injury people, or some people they just cannot speak. So this market, I will see probably the easiest commercial adoption of BCI technology. I would like to define the developing of the roadmap of BCI technology into 4 different levels. For example, level 1 is motor control. The level 2 is language synthesis. The level 3 is going to be the vision restoration, and the level 4 and the ultimate goal is the memory uploading and downloading. So in the long term, for all 4 levels, might take 20, 30 years. But for the first 2 and the level 1, level 2, even the level 3, I would say they're probably less than 10 years.